Hello, everyone, and welcome to the Wind Energy Science Leadership Series, Atmospheric Science for Wind Energy. My name is Alex Lemke, and I'll be your facilitator today. And today's webinar is the third in an ongoing series of educational webinars that include presentations and discussions on wind energy related topics. Features speakers from the National Renewable Energy Laboratory, academia, and even our industry partners typically join these webinars to discuss the challenges facing wind energy and the pathways forward for making wind one of the most prevalent energy sources of the future. Today, we begin with a panel of wind energy science and technology leaders for a webinar about cutting-edge atmospheric science research informing wind energy today. Before we begin, I have a few housekeeping items to cover. First, today's webinar will be recorded and available on demand and will be posted online. Please be sure to mute your phone lines and turn off your cameras if you're not speaking. And next, we encourage you to use the chat feature to ask questions, and we will be answering those questions at the end of the session. If we do not get to your question today during the webinar, we will be sure to follow up afterward. And finally, I would like to ask Peter Green, the Deputy Laboratory Director for Science and Technology and the Chief Research Officer for NREL, to say a few words before we begin. Peter?
Okay, thank you, Alex. Good morning, everyone, and welcome to the series on science of wind energy. I'm glad to see that we have lots of participants here this morning, so really thank you for joining. Yeah, I've been a big fan of wind energy long before I even came to NREL. I've been pretty enthusiastic about this field. And the one thing I can say now with a lot of certainty is that this is perhaps the most exciting time in the field of wind energy. And I think it's also the most pivotal time. The good news over the last decade or so, we've seen an order of magnitude drop in the levelized cost of energy for wind. It's now comparable to conventional forms, and as well as its competitor solar, in some cases even cheaper. There's some exciting things going on. You know, the Siemens Gamesa wind turbine of 14 megawatts and rotor of 220 meters, which is a big deal. This morning I was reading that they're now connecting wind turbines to electrolyzers to make hydrogen directly. Shell is doing the same thing. And so I think this is a really exciting time with a lot of possibilities. The reason I say it's pivotal is that in the next 20 years, renewables are going to occupy a major proportion of power production on the grid, which means that wind is going to have to increase production capacity by an order of magnitude, producing many terawatts of power. So that's a challenge. It's a challenge for you guys. You know, the paper you published as a group in Science really talked about what are some of the scientific challenges that need to be met for that. And it's real and it's really important, and it's glad to see that this community has come together to do this, as did the solar community. There's other parts of the science and engineering community. It's a challenge for you because all the other communities are really pushing hard to make sure that they also have a major play in the years to come in terms of power generation on the grid. So I see this is an exciting time. You're competing. You're going to be competing with all the other sources. The fossil energy guys aren't going away. The guys in nuclear power are talking about producing hydrogen from heat from nuclear plants are doing that lately. So I'd say this is an exciting time. And so I'm looking forward to more of this seminar series as we go along. And so with this, let me thank you. And again, it's exciting to see so many people, like almost 50 online for this this series. Okay, take care then.
Thank you so much, Peter. And thank you to our esteemed panel of speakers who will be speaking today. First, I would like to introduce Julie Lundquist, who is a professor of atmospheric and oceanic sciences at the University of Colorado Boulder and a joint appointee at NREL. She will be addressing some of the interesting interactions between the atmosphere and the wind energy. Carolina Draxel is a senior researcher at NREL and will present on various atmospheric science related projects that promote wind energy research and deployment. Mike Optis is a senior atmospheric scientist and will be discussing NREL's recent efforts to leverage machine learning and uncertainty quantification to improve wind resource characterization. And finally, Pat Moriarty is a senior researcher and will give an overview of a large-scale field campaign focused on wind plant-atmosphere interactions called Awaken. I'd like to turn it over to Julie.
Thank you, Alex. And thank you to all of you who made time to join us for our discussion this morning. There's a lot of really exciting open questions in atmospheric science and wind energy, and we hope to trigger your interest and start an ongoing discussion. So one of the first questions that people often ask me is, well, wait a minute, you guys have been doing weather forecasting for 100 years. Why do we still need to answer some atmospheric science questions in the context of wind energy? And part of the challenge is that, of course, weather forecasting has evolved over the last 100 years. And here we have some nice pictures back from the 1940s and 1950s showing how weather forecasting was all done by hand at that time. And now weather forecasting is a very automated enterprise where we have data streaming in from satellites all over the world, surface stations all over the world. And all of these data are assimilated together into numerical weather prediction models that we use to predict the weather. And of course, the wind, the resource for wind energy, is part of this forecasting. And we like to think about the entire global circulation when we run these numerical weather prediction models, because of course we're not forecasting just for one particular wind farm. Each individual wind farm is experiencing the entire large-scale flow around the globe, and of course there are consistent patterns that we tend to see. So for example, in the mid-latitudes between 30 degrees and 60 degrees north and 30 degrees and 60 degrees south, we tend to have westerlies, but there are often fluctuations, as we know from our own experience with the weather, that go beyond the equations that describe the global circulation. So if we want to think about those particular equations, I'm not going to ask you any quiz questions or anything like that about these equations. I just want you to understand that we have equations that describe fluid motion. We take those equations and we discretize them onto a grid, as pictured over here on the side, where we break up the atmosphere into both horizontal grid cells and vertical grid cells. And then we try to represent physical processes. And so we need to assimilate observations from satellites and from surface-based measurements and aircraft measurements as well. And then we move these equations forward and march them forward in time in order to solve what we expect to happen with temperature, with pressure, and importantly for wind energy, with winds. Now the challenge is, although weather forecasting has improved quite a bit in recent years, we actually need different things for wind energy than we do for normal weather predictions. So in the wind energy application, we need to think about the winds between about 30 meters above the surface and 200 meters above the surface for current wind turbines. And as we move to the larger scale turbines that Peter Green was mentioning earlier, we'll need to look at even higher altitudes. So that's what the turbine wants to see. But forecast models were actually designed to forecast temperature and precipitation and winds close to the surface where people are. So we're using numerical weather prediction models for wind energy applications, although those models were not designed specifically to predict what we need for wind energy. So there's a lot of work that's rapidly happening right now where we are focusing on these upper altitudes for wind energy purposes. And sometimes things that worked at the surface do not work at higher altitudes. So if we want to think about what we need for wind energy forecasting, we have to couple weather scale phenomena like this frontal passage that just moved through this domain of wind turbines, changing the wind direction and changing the direction of propagation of wakes. We need to couple those weather scale phenomena with the finely resolved simulation parameterizations and the fine scale features of wind turbines and their wakes that are not represented in numerical weather prediction models. So there's a coupling of scales. We have very coarse scales where the weather is predicted on scales of horizontal resolutions of 1 kilometer or larger, and wind turbine phenomena need to be resolved at much more fine resolution, because if we look at the individual wakes from these individual turbines, the details of how they move and how they affect each other are really, really important. And some of the later speakers will be talking about wake steering and other types of technology where we need to represent those fine scale features. Okay, I'm trying to move on to the next slide. So if we think about what happens within an individual wind farm and how the atmosphere affects flow in the individual wind farm, here I have an example of 3 wind farms in Texas, where we're trying to understand how the atmospheric conditions, the wind speed and the wind direction, and very importantly, the temperature stratification or the atmospheric stability, how that affects the development of a wake, a region of slow air downstream of a wind farm, and then how that wake affects a neighboring wind farm. So over here on the left, I have kind of a plan view with the colors denoting the wind speed deficit caused by one particular wind farm and then how that might affect a downwind wind farm. Over here on the right, we actually have the same simulation but gridded so that the colors represent the power deficit at a downwind wind farm because of the presence of the upwind wind farm. So now I'm going to start the simulation and you'll see how the wind, which is initially from the southwest, will move around and change direction, and the colors over here will indicate the power deficit at the downwind wind farm. And there's some interesting variations caused by the atmosphere that will be important to note. So you can see that sometimes the wind speed deficit is very large. It moves back and forth, it meanders a lot like a smoke plume would, and then that influences the power production at the downwind wind farm. So this area of wake interactions is one of the really interesting areas of where atmospheric science and wind energy are working together. Because information about these wakes, you can make an annual average or a monthly average, but there are a lot of very important details about the daily cycle of these wakes and how they vary. So for example, when we move to the next slide, before I move on to the next slide, I want to point out that if this downwind wind farm had not had an upwind neighbor, it would have had a capacity factor of around 40%, but because of the upwind wind farm, the capacity factor over the course of this entire month dropped down to 36%, and that has a very immediate impact on the profits that were generated by the downwind wind farm. So understanding how the atmosphere interacts with wind farms and how that interacts with power production is very important and is kind of a hot area of research right now. So if we want to understand why these power loss events happen, we can take these types of simulations and break them down, slice and dice them into different ways. And so what we see here on the x-axis is a measurement of the surface heat flux. So this is something that atmospheric scientists get concerned about. And this is basically how much the surface is heating the atmosphere. So during the day, we have positive values. At night, we have negative values because the surface is cold and cooling the atmosphere. Each of these dots represents 1 hour in our month-long simulation, and the colors represent the wind direction at the time. The size of the dot represents the total power deficit. So what we see here is that all of the big power deficits at this particular wind farm happened during a certain wind speed regime and happened at night. So this is really important because this helps us understand and predict wind farm wakes and how wakes are interacting with the atmosphere. So this is just one example of how atmospheric science and wind energy are working together. Because if we can understand when strong wakes will occur, we can anticipate them, and therefore we can manage them as we integrate larger and larger amounts of wind-generated electricity into the power grid. So that was a case in flat terrain in Texas. So here's an example where we're looking at terrain contours. So this is a map view of a wind farm. The dots represent individual turbines. And we're looking at a wind farm in the Columbia River Gorge region. And these, again, are simulations. So the blue represents the Columbia River, brown represents high altitude. And you can see that these turbines are periodically generating large wakes. So right now, there's not much of a wake because this is daytime convective conditions. And as we just saw, during convection, we don't have wakes. But when night comes, we have a very strong wake that is generated. So we have a lot of dark blue values indicating strong wind speed deficits. But do you remember how in that Texas case, the wakes just tended to move directly downstream? Here we see this amazing example of how the wake gets channeled by a relatively shallow river valley that is one of the tributaries of the Columbia River Gorge. And so this means that when we look at wind farms interacting in complex terrain, we need to pay much more attention to how the atmosphere and the complex terrain and the wind turbines are interacting. So we have a lot of interesting research going forward to see how we can best represent these phenomena and then account for them when we integrate renewably generated electricity into the power grid. Okay, so finally, I'd like to point out that we have a lot of exciting work that will be coming up as we look into offshore wind energy in the United States. And we've just talked about flat terrain versus complex terrain. When we're looking, we probably need to think about new phenomena like sea surface temperature that is particularly important when we look off the east coast of the United States. Sea surface temperature also varies in Northern Europe and other parts of the world where offshore wind energy is regularly used. However, the variations that we have in sea surface temperature off the East Coast, as seen here in this visualization, are very dramatic and very intense and will probably trigger more complex and more interesting wind flow phenomena than we have actually explored in the offshore wind energy world before. So as we move forward through this seminar, I think that Carolina Draxel will also be talking about offshore wind energy and some of the exciting open questions that we have when we think about atmosphere and wind turbine interaction, and then when we get into ocean surface and atmosphere interaction, and when we fold wind turbines into that as well. There are just so many exciting questions that will be exciting to explore. So with that, I think I will hand it over to Carolina.
Draxel, and I'm a senior researcher at NREL and the technical lead for atmospheric science for wind energy. My background is in mesoscale atmospheric modeling. And I'm now going to talk about how NREL translates the atmospheric principles that Julie talked about into practical projects. And so first, I want to introduce the 4 pillars that our atmospheric science work is based on. So the first one is resource, site characterization, and forecasting. And here, scientists at NREL are leading efforts in numerical weather prediction for renewable energy, resource assessments, remote sensing, and forecasting. The second pillar is about oceanographic and meteorological processes. So this is basically our met-ocean or offshore atmospheric science component. And here we improve the understanding of the physical, meteorological, and oceanographic processes that affect the wind resource characterization offshore. Then third, the pillar is about global weather, mesoscale, and plant level effects and how these interact with each other. And here, NREL scientists study the impact of atmospheric flow on turbulence and power output of wind power plants. And the last pillar is about visualizations, and here we visualize large and complex data sets to communicate the results of our projects. And so now in the following slides, I'm going to pick out some examples of what we do in these pillars. First, I'm going to start with wind resource assessments. So wind resource assessments have historically been maps, and they exist for various countries and are for a certain hub height. And in 2013 at NREL, we went a step further and created the Wind Toolkit, which is a time series dataset covering 8 years from 2007 to 14, with model output over the US every 5 minutes for every 20 meters up to 200 meters in the vertical. And it's freely available online. Here on the bottom, you can see the link. And we also created power forecasts for selected sites. And this is a great data set, and it's used by many across the world. But stakeholders have been requesting a data set that is longer and covers about 20 years. And also, so this data set is a deterministic data set, meaning that it is one solution of many possible. So it's a simulation based on WRF. And if you change the settings of WRF slightly, for example, you change the boundary layer scheme, you get slightly different results. And so here's an example of the challenge you can run into with a deterministic model output. So these are 100-meter average wind speeds offshore. And you see a small belt near the coast, which is model output from an industry partner whose dataset we bought at high resolution. And the thick belt is the average Wind Toolkit output. And you see a discrepancy between the two. And in some locations, you might ask yourself, oh, what is the wind speed actually? And which one of these is right? And so in the absence of data offshore, we can validate against, we don't know. And so we have an estimate of what's the best solution, but ultimately we don't know the exact answer. So our plan is to update this data set to cover 20 years and include Hawaii and Alaska, because those were not included in the first round. And also we want to include uncertainty information. And Mike Optis will talk about how we're going to create this uncertainty information. So now I want to give you a flavor of what the new data set will help with. So first, it will support the distributed wind community by giving them access to a data set that covers all heights above ground, also the lower ones that the distributed wind community is interested in. Then it will help with the development of a computational framework for assessing eagle risk near wind farms. So we want to know where the eagles soar across the US to avoid fatalities. And we also want to support the offshore wind energy. So there are a lot of lease areas off the east coast of the United States where wind farms will be deployed, and Mike Optis will also talk more about this. So as I said, we've created wind resource assessments and grid integration datasets for various countries, for example, the Philippines, India, Vietnam, Mexico, and Canada. So with Mexico and Canada and the US, we covered the whole North American continent for a grid integration study. We model over Kazakhstan and the surrounding countries. And one example I want to show here is Bangladesh, where we had a measurement campaign as well. So we went into the country and installed met masts and 2 SODARs, and we engaged the locals, the local community. And we also created a 3-year-long data set. And developers can now use this data set for free, as can anyone else. And developers can then create a market in Bangladesh. And now I want to talk about forecasting and present the second wind forecast improvement project. And this was a project that we collaborated with other national labs and NCAR and NOAA, and also a lot of industry partners. So the goal of this project was to improve wind speed forecasts in the turbine rotor layer in complex terrain. And this was done by improving model physical parameterizations and numerical methods. The study area was in the Columbia River Gorge, here between Oregon and Washington, where a wealth of observations was deployed. And if we zoom into the gray box, we see the layout of the wind farms in that area in white. And the Cascade Mountains are right at the left border of this map. And the 2 major mountains, Mount Adams, Mount Hood, are here. And then there's the Columbia River that cuts through the Cascade Mountains and creates the Columbia River Gorge. And this whole area exhibits a lot of interesting weather phenomena. And here's a graph that shows the number of occurrences for phenomena that occurred in the Columbia River Basin during the 18-month field campaign. And we see that the gap flows occurred the most, followed by cold pools, and mountain waves occurred about 100 times, also topographic wakes, and they often occur simultaneously. And in the following slides, I want to give an example of mountain waves because they impact wind farms. And this has not been presented in the literature so far, but it's very important for wind energy. So this is a movie of simulated wind speeds at 100 meters with WRF. So here this triangle is Mount Hood, down the next one is Mount Jefferson, and the square is the location of a wind farm. And the wind comes in from the west over the mountains and creates these stripes. So yellow, high wind speeds, blue, lower wind speeds, and those are mountain waves. And if we take a snapshot of a time when these waves happened, and we compare that to a satellite image, and we were lucky that at that time there were clouds, so we can actually see them, then the waves are pretty similar. And if we compare the wavelength of these two, they are in both cases about 10 kilometers. And we also see nice interference patterns of the highest mountains. And here I want to show you that the mountain waves impact farm output and show variations in total farm output. So this graph has percent of rated power here on the y-axis and axis time. So the green line is the power output of one wind farm in the area, and we see fluctuations during a certain time. This was when mountain waves were present, and those are about fluctuations near full power, and the power fluctuates by about 15%, and that's a big deal. And so the other lines are power output from other wind farms. So they didn't go all the way to rated power, but they still show fluctuations. And so we conclude, and we have a paper out here, the link is up here for discussion in wind energy science. So we conclude that mountain waves should be considered when building wind farms in complex terrain, because mountain waves impact the amount and location of the west wind resource. Now I want to move on to the second pillar, the oceanographic and meteorological processes one, and talk about the third wind forecast improvement project. And that's also known as the Offshore Wind Resource Science Project. The UE is investing in offshore wind resource science to support the development of offshore wind energy in the United States. And as a first step, a workshop was held in March 2019 to have representatives of the offshore wind industry and marine environmental research community share views on met-ocean information needed to successfully develop offshore wind projects in the United States, and also to identify current knowledge gaps. And so we have a report out, and here's the link. It says available for free for everyone. And the key science challenges identified were stably stratified atmospheric conditions, the depth of the marine atmospheric boundary layer, the depth and characteristics of the surface layer, wind shear across the rotor layer, fully coupled wind, wave, and wake models, and model validation with uncertainty quantification. And in response to this workshop, DOE drafted a funding opportunity announcement for a project that will improve wind resource modeling and forecasting in offshore wind energy development areas. And similar to WFIP2, this will also be done by improving model physics for foundational wind forecasts and other applications in offshore wind energy areas. So that means basically that DOE will fund a huge field campaign offshore off the US East Coast where wind energy development areas are. And the observations will be used to advance our understanding of the marine atmospheric boundary layer and mid-ocean parameters. And last but not least, I want to talk a little bit about the global weather, mesoscale, and plant level effects and the work we do in this area. So when we talk about models, we have to consider the scale that they cover, and usually certain types of models are good at a certain scale. And if we go down in scale and all the way down to the microscale and model what a turbine sees, we need to bridge the different scales to have the weather information trickle all the way down to the smallest scales. So for example, as you see here, like global models, they predict large scale weather circulation. And then we can go down to the mesoscale to predict regional features and go further down to what a wind plant sees. Here, for example, this is the same graph that Julie shows. We have flow, and then a cold front comes in and completely changes the wind direction to flow field. Or then we can go a step down and see what the turbine sees. So right now we go from the larger scales to the smaller scales, and hopefully in the future we can do some research and go from the smaller scales to the larger scales and see how wind farms impact the atmosphere. And we have actually a DOE-funded project, the Meso-Microcoupling project, where we do exactly that. So we, the aim here is to simulate the wind flow within wind farms as realistically as possible. And this will improve wind turbine design and inform operation strategies. And with that, I'm going to hand over to Mike Octus. Thank you.
Thanks, Carolina. So I'm going to spend just a few minutes talking about how NREL is leveraging machine learning and uncertainty quantification tools for improved wind resource characterization. I wanted to start by discussing the potential benefits of these tools. And as Julie and Carolina have mentioned in their talks, the atmosphere is complex, existing on multiple scales, with processes we are only beginning to understand, so our knowledge is certainly still imperfect. And as they both discussed too, the physical models that we use to try to describe the atmosphere are approximations with their own limitations. So we have these series of equations we try to use to represent the atmosphere, and we try to represent for numerical weather prediction models how those interactions exchange with each other on a 3D type grid. So our best representation of reality with its limitations. And so with those in mind, tools like machine learning can be used now to identify relationships that maybe we don't yet understand or have available, either through physical measurements or analytical equations. And in the same light, uncertainty quantification, or UQ, can help us understand the limits of those models and help gauge our confidence in what we're representing. So just to do a quick crash course in what machine learning and uncertainty quantification mean in the context of wind energy science, let's first start with a definition from Wikipedia, which says that machine learning is the study of computer algorithms that improve automatically through experience. So it's a bit abstract, a bit general. I think in the context of what we use it for, the word experience is really referring to having more data. And by improve, we're talking about the ability to make better predictions. So a very high level example of this, these concepts at work would be looking at maybe contrasting a lot of data and less data when looking at linear regression. So suppose we had wind speed on one axis and we had energy production from a wind farm on another. You can see with a few data points, if we try to draw a line of best fit through there, there's quite a lot of variability and a lot of uncertainty in what that line of best fit might actually be. Whereas if we had a lot more data points, we see that the relationship is much more clear. We're able to, with more confidence, draw a line of best fit through that data. So that's all we mean when we talk about experience, more data, better predictions. So it may seem a little weird that I'm talking about linear regression in the context of machine learning, but in fact, yes, linear regression by definition is a type of machine learning algorithm. Of course, that's not how we usually discuss machine learning today. When we discuss it, we're usually referring to more complex and computationally expensive algorithms. So without going through an exhaustive list, this would include things like regression trees, for example, or neural networks. And there's a lot more I could talk about, but we don't really have the time. But a key feature of modern machine learning algorithms is their ability to allow for multiple inputs and have multiple outputs, so predictors or predicand. And that allows for the construction of very complex statistical relationships that you might not otherwise pull out from more basic equations. The big drawback or criticism, of course, is what's known as this black box problem. The idea that we put all these inputs into the algorithm, all these outputs come out, we don't really understand what happens in between that. Despite that, these algorithms do have very high level of predictive power that we've been leveraging. It's also worth noting a lot of these aren't new. They've actually been around for a long time, and it's only with modern computing power, whether through high performance computing resources or just modern laptops, that has allowed for these algorithms to finally have widespread use across all fields, not just wind energy science, of course. So quickly on pivoting to uncertainty quantification, if we wanted to pull the Wikipedia definition, it would be determining the likelihood of certain outcomes if some aspect of the system is not exactly known. So again, a bit general and abstract. In the context of what we really care about, we're really trying to answer the question, how confident are we in our measured or modeled results? So the types of questions we might answer they vary quite a lot. We could be interested in how sensitive the model is to inputs, how accurate are my measurements, and just more of these types of questions as we try to measure the wind resource and model it on different scales. So with that crash course over, I wanted to spend just the next part of this presentation just highlighting a few areas where we've been applying machine learning and uncertainty quantification here at NREL. This is certainly not exhaustive, but just should give you a sense of what we've been doing. The first area has been in wind speed extrapolation. So we talked a lot about the offshore wind resource and the emerging offshore wind energy industry. And we know that we have a lot of surface measurements offshore. These include satellite measurements, where satellites in space can measure surface wind speeds based on the ripples in the water. And also a large network of offshore buoys that are publicly available and measure wind speed a few heights above the surface. So traditional techniques to try to take these winds and put them up to hub height usually rely on very simplified models. So things you might have heard of include the power law or logarithmic profile. And these equations are fundamentally limited in that they assume a specific mathematical fit across the whole height of interest. And their assumptions are frequently violated, especially offshore, as we're starting to see. So what we've been doing at NREL is trying to see how machine learning could actually supplant these more traditional models and provide more accurate results. And so it's as simple as taking the variables we have at a buoy, for example, be it wind speed, wind direction, air temperature, sea surface temperature. And with measurements at hub height, for example, from a floating LiDAR, we can develop an algorithm to predict those hub height wind speeds based on surface measurements. And we have an article that came out for the onshore examination, and we're also looking at an offshore publication in the next year or so. But we're finding significant improvements relative to traditional techniques. Moving on to the role of modeled wind speeds. So Julie and Carolina both talked a lot about numerical weather prediction models and how we have wind resource estimates coming from those. So if, for example, let's look at a sample 4-day period, and this is wind speed from a numerical weather prediction model that shows a nice ramp event, for example. And just for comparison, we run that through a 15 megawatt offshore IEC power curve to give you a sense of what the power production might look like. And you can see we reach peak power once we reach that peak in wind speed. So about a decade at least of research has shown that these NWP models can be quite sensitive to the inputs and setup within that. And we can test that out by running another model over this space, but with slightly different inputs and setup. And in orange, we see the differences. So you can see slight differences here. It measures a peak and then a decrease in the wind speed. And this translates to a much larger difference in power, especially in this region. And you can see too how this actually drops off due to cutoff wind speed and estimates zero power for a bit. If we continue this and implement what's known as an ensemble approach, we can run a lot of different model setups, and then a much more clear picture of ensemble variability comes into play, and we can begin to assess the confidence we might have in our NWP modeled outputs by calculating something like the standard deviation in wind speeds being shown there. So this is the approach we've been implementing for our new 20-year offshore wind resource data sets that are going to be a replacement to the wind toolkit. The challenge, though, is we are trying to run these ensemble-based numerical weather prediction runs, but they're very computationally expensive. And we're trying to marry that with the fact that we're trying to run these long-term 20-year data sets, and we don't really have the computing power to run 20-year WRF simulations again and again and again. So this is where machine learning has come in. And what we end up doing is extrapolating uncertainty measured over a shorter period over to the longer period. So for example, in blue here would be the usual ensembles that we're running, and we would pick from that ensemble one setup that validated best against observations, which we're showing in orange. We would then run that single model setup for the full 20 years. And then based on the variability we're seeing in this shorter time frame, let's say a year, we would train a machine learning model to predict what that variability is based on the atmospheric variables within that single model run. And once that machine learning model is trained, we can apply it throughout and be able to calculate this band showing here. So this is what we've been doing for our next generation wind resource data sets. I have an example for California to show here on how we would actually calculate and disseminate this information. So here we're showing the sensitivity in the modeled annual mean 100-meter wind resource for offshore and onshore California and a bit part of the other states. So again, this is based on the standard deviation divided by the mean, or the coefficient of variation. And we can see that it varies between 0 and about 12% variability based on purely on the sensitivity in our numerical weather prediction model setup. We see much higher sensitivity in pockets onshore, and also in terms of offshore, closer sensitivity to the coast. And in red, we're showing these proposed call areas for offshore wind energy in California. So as I said, these models are very expensive. And if we thought about wanting to run global models, for example, this becomes a bit restrictive. And so I wanted to touch on one exciting project going on at NREL that asks the question if we always will need NWP models to downscale the wind resource. And what I mean is by downscaling is essentially what a numerical weather prediction model does, is takes coarse resolution from a global model, draws a box around an area of interest, and then runs this at higher resolution to produce better output. So a nice, interesting question being asked at NREL is whether machine learning can be used instead. And in particular, Ryan King and his team down at the NREL Computational Science Center have been doing some really cool work trying to address this question. And it's based on this idea of super resolution, where you can take an image that's pretty blurry and having been trained on many other images in the past can actually refine that and make a nice high resolution image. And they've been asking whether that same concept can be applied to coarser global climate models or global atmospheric products. And the results have been pretty promising. For example, shown here, where if you train on enough data, you can take what is a coarse resolution model here and turn it into a much higher resolution model, which resolves at a very fine resolution some of the turbulence features that Julie and Carolina have been talking about. So some pretty cool stuff overall. This is only a very small snapshot of the work we're doing in this space. Hopefully gave you a sense on what machine learning and uncertainty quantification can do. So thanks for that. And I will pass it on to Pat.
Okay, thanks, Mike. So I'm going to be talking about the American Wake experiment. We've been talking a lot over the seminar about simulations, but of course we also need observations to be able to look at what's actually happening in the atmosphere and where our models are predicting what's happening in the atmosphere correctly and incorrectly, so that we can better improve those models for future use. And also the American Wake experiment obviously focuses on wakes, which are at the smaller scale of the atmospheric side, where we're looking at wind farm wakes and even individual turbine wakes and how they interact with the atmosphere as a whole. So I'll also start off with a simple definition. Maybe many of you know what wakes are, but and Julie spoke about wind farm wakes in particular. But according to Merriam-Webster, a wake is the track left by a moving body in a fluid. So this definition fits fairly well with things like ships and aircraft, and even this duck, as you see in this graphic. But obviously in wind energy, the body is not moving, but the fluid is. So the wind is blowing past a wind turbine, much like this building here. You can see the wind blowing past the fluid, and then behind the body, there's a wake, which is an area of low wind speed and highly turbulent flow. And this happens at many scales around the universe even. You can see in the lower left-hand corner here, islands that are producing wakes just from the wind moving past them, or even the Earth producing a wake in the solar wind behind it. But of course, we're interested in wind energy. And one of the big reasons that we're interested in wakes for industry, for wind energy, is the energy that's lost due to wakes. So in a typical wind plant, about 100 megawatts in size or larger, we'll see about 10% of that energy is lost due to just wake interactions. And here on the bottom, you can see a really highly detailed simulation of a wake, the blue area being the low, highly turbulent wake area, and the red air above being the free stream coming into the wind farm. Because when we place wind turbines within wind farms, they're always going to interact, and there's always going to be some loss due to wakes. But through things like wind farm control, which Julie mentioned, we might be able to reduce this loss significantly. I'm not sure that we'll be able to 100% eliminate this loss, but through better understanding of wakes, this overall loss can certainly be reduced. Perhaps more importantly is the uncertainty of the current generation of wake models. So in industries, if you're a wind farm developer, before a wind farm is built, your goal is to predict how much energy the wind farm will produce over its entire lifetime. And the models that are currently used by industry are highly uncertain. So here you can see that anywhere between 20 and 50% variability in that overall energy loss model, meaning that the actual predicted energy loss is anywhere between 2 to 5% plus or minus from your predicted value. Just to give you an idea of how significant that is, the typical profit margin for a wind farm owner is about 3%. So the uncertainty for a wind farm or for predicting the overall energy production using these industry models is actually plus or minus the profit margin for a wind farm owner. So less than ideal. And we do hope that through better understanding of wind farm interactions with the atmosphere that we can reduce this significantly, and certainly less than 5% we think is possible. So these predictions, just to give you another example, have real world financial consequences. Back in October, Ørsted, which is one of the largest, if not the largest, offshore wind farm developer in Europe, released a press announcement where they basically said that they were readjusting their energy estimates across their fleet by about 2%. Shortly after they released this announcement, their share price dropped considerably, so about 8% within a few minutes. So the markets panicked, and actually this announcement sent some shockwaves across the wind industry as a whole. where everyone is now trying to figure out how to adjust their own fleet estimates. And in this press release, they also stated that the primary reasons for this, again, are wakes and the models that they use to model the wakes, and blockage. And so blockage being kind of an upstream effect where the wind farm reduces the velocity of the wind before it actually impacts the wind farm itself. So very related, and the focus of the Awaken project going forward. These two effects will be looked at in detail. Another thing about that press release is they stated this is an industry-wide issue. So that gives credence to a national laboratory being involved, in that we would like to help the entire industry better understand these losses, so that we can help eliminate any overestimates that might happen in the future. Okay, so Awaken, what is it? American Wake Experiment, obviously it's an experiment, a large-scale field campaign. It's really an international effort, so we have collaborators from Europe and Canada at the moment, with lots of different instrumentation coming, but using both observations and also simulations to really better understand what's going on within wind plants and how they interact with the atmosphere. This will be located in the central United States, and I'll give you more details on where exactly. But in the wind belt of the United States, where the vast majority of wind farms are installed. We also hope that these will be some of the most detailed wind plant observations to date. And you can see a graphic here on the bottom of an example of what we'll be looking at. So here's just some turbines with different wakes. We have heating from the ground that changes the atmospheric stability depending on time of day. And to observe those, we'll have things like scanning lidars, looking across the wind farm, and even aircraft flying behind wind farms to measure the overall impact of the wind farm wake, which, if you look at the top view of this wind farm, might look something like this, with the brighter colors being higher wind speed and the darker colors being individual turbine wakes that form an overall wake. So if you'd like to know more detail about the Awaken experiment, we do have a wiki that's consistently updated, and you can find lots of details here about science goals and also the timeline of when instruments will be deployed in the field. A little bit more detail about where exactly we'll be located. So the Awaken project will happen in and around the wind farms in Oklahoma, northern Oklahoma. And one of the main reasons that we're looking into this area is a site that's actually run by the Department of Energy Atmospheric Radiation and Measurement Program. And this site was constructed in the early 1990s. And its primary mission is to gather atmospheric data for validation of climate models. And so they do tend to focus a lot on clouds and cloud interaction with the surface. But of course, there's lots of different atmospheric measurements that are valuable for both the ARM program, but then also applicable for wind energy. And here in this graphic, the different color dots are actually measurement sites that are maintained by the ARM program, whereas the blue dots are actually wind turbines. And these wind farms were not built until about 2012. So ARM also is going to benefit from this program in that the impacts of the wind farms themselves on the measurements at this DOE ARM site are not yet quantified. So it's really a mutually beneficial relationship where we can use the ARM instrumentation to observe what's happening in the wakes of all these different wind farms. And then in turn, we'll be able to tell them how the wind farms are impacting their instruments since the wind farms have been constructed. So in addition to the ARM measurements, we'll have lots of different collaborator instruments involved. with, at the moment, over 100 different instruments, all kinds of instrumentation. Some examples of what we'll be using are here. So really state-of-the-art instrumentation available to the wind industry at the moment. And many of these are even research-grade instruments that aren't necessarily available for purchase. So scanning LiDARs are good for looking at individual or multiple turbine wakes within a wind farm. You can see some example of a dual Doppler system here. So at the moment, we have about 20 scanning LiDAR systems to be deployed out in the fields. Over on the right here, we have the Texas Tech dual Doppler X-band radar system. And here you can see an example of a similar system that was used to measure wind farms here. And in this graphic, the little black dots are the turbines. The blue areas are the wakes from those turbines. So really detailed observations across multiple turbines. And then at the larger scale, we'll be using aircraft. So down here in the lower left-hand corner is actually an ARM aerial facility. It's an unmanned vehicle called the Arctic Shark. And here's a different example of a field campaign that took place in the North Sea, where an aircraft actually flew along this line and was able to measure the overall wake of 2 wind farms very close to each other. So you can see here the overall wake of a wind farm, which is extending at least 30 kilometers, perhaps 50 kilometers downwind. So wind being the primary quantity of interest, but we're also interested in observing other atmospheric quantities to figure out what else is going on in the atmosphere. So here's an example of an ASSIST thermodynamic profiling system. And there we can get temperature profiles and look at things like humidity, and then figure out how we can validate our models and see what the impacts of the wind farms on those observations would be. Once we have all these observations, and in conjunction with simulations, then we can get a deep and better understanding of what's actually going on within the wind farm. Here's a blow up of that graphic I showed in one of my previous slides. But you can see that the flow through a wind farm is fairly complicated, with these white lines being individual turbines. You can see the wakes behind them. They're meandering, they're merging with other downstream wakes, and then all combining into an overall large-scale wind farm wake downstream. And of course, all of these wakes are moving in time and space because the wind is always changing speed and direction. So very complicated, not only in space, but in time. And then we can use these observations to better validate and improve our models. Here's an example from a study that we finished earlier in the year, looking at an individual turbine wake, the observations of which are these little black circles, and then lots of different simulation tools of different fidelity. And how does each of these models compare to the validation data, and why are there differences in models? So just better understanding, why do these models work, and which models work best and why. And then I think this is my last slide. So the timeline for the field campaign, we're doing lots of different planning at the moment for the Awaken project. And it will be kicking off at the beginning of 2020. So in January of 2020, we hope to start our long-term observations. So instrumentation that can be left out in the field for long periods of time. And then in 23, we'll have a shorter, very focused field campaign looking at very fine detailed physical things, but also with instrumentation that cannot be deployed for long periods of time, like aircraft and drones and things like that. We do welcome additional participation. So if folks are interested inside and outside of NREL, actually, with a caveat that funding is limited. But everyone is also welcome to participate in our monthly update meetings if you'd like to learn more. And we also do have different working groups helping us design the field campaign at the moment. And again, there's our wiki link if you'd like to add or find out more detail. Okay, so I will stop there.
Thank you, Patrick. We're going to move over to Q&A. There's a couple of questions in the chat box, and we encourage everybody else to take advantage of that and put your questions there. Pat, can you see the chat box? There's a couple from Bryant Bueller.
Yep, I saw that one. And I will direct this one to, how about Carolina? Seems that optimal wind locations vary based on location. When does it make sense to make the windmill or wind turbine mobile in order to move to the area with most wind? Borrowing from some thinking in robotics.
Yeah, this is a very interesting question, and I think it also touches upon the structure of a turbine, which is not my area of expertise, but I can think that if you, excuse me, if you move a turbine, how do you make sure its foundation is right? Because I mean, now they have concrete foundations, and I don't know how this will work if it has. I don't know how you would move it. I mean, it's just structurally or just practically. I mean, Brian, can you elaborate on what you were thinking, how this would look like? Would it have wheels? And then I was just thinking, you know, the loads in a turbine, which is, how would you make sure it's really standing at the end where you want it?
I hope you can hear. I hope you guys can hear me all right. This is Brian. Yeah, so I've just been doing some general research on like swarm robotics and things like that. And as far as space-based applications and a lot of energy applications, that seems to be where things are going. Just that the opportunity to harness energy is often mobile, right? It's usually not just concentrated in one place. It changes throughout the course of a day. So that's, I don't know the answer to the question. I was kind of just throwing it out there. Like, when is the breaking point? When do you see such a opportunity to harness so much more energy in one location versus another that you do decide that it's better to be mobile? Much like you see a lot of times in like the transportation industry, where there's an energy differential or a greater opportunity for people to commute to work in one area but to live in another. When do we reach that breaking point where we say, hey, the energy is so variable, whether it's like I'm mainly thinking in a coastal ocean harvesting, where the winds are, I believe, optimal from the research I've seen. So I was just posing a question. I don't have the answer to it, but I definitely see that being where things are going, where we don't have, static systems that are, anchored in one place consistently, but where we can sense that there's an opportunity to harness energy in one location more so than the other. We do the calculation to say it costs us this energy to move from point A to point B, and then we move to point B and harness energy there if there's a better opportunity.
Yeah, I think it's definitely a good thought. There has been some thinking about that at NREL. Walt Musial in our group in particular has been thinking about an offshore design that actually roves with the wind. So it can be pushed around the wind or around the ocean through currents or even the wind, producing hydrogen, and then ships will come and pick up the fuel. So that it's probably easier to move it offshore. And Julie chimed in on the chat here too. Also a possibility with airborne wind. We know that the military has interest in this in particular, and has been funding different projects where there are mobile systems that can be easily deployed. Yeah, in different areas. So yeah, I think it's a good thought for sure. But a typical utility wind turbine is difficult to move around. Although people have talked about within wind farms having them mounted on railroad cars, mainly to reduce the wake interactions.
Okay, if I could get more, I'd like to read more about the gentleman that you just referenced. So if I could, that was talking about doing the hydrogen storage and stuff. If you could please put something in the chat or anything where I can reach out to him or read more about his work, I'd greatly appreciate it. And thank you for your answer and the presentation.
Sure. Yeah. And you had another question about what are the factors that most directly contribute to optimal wind power production? How about Julie, take that one on?
Sure. So I think that when we think about optimal wind power production, we generally focus on wind speeds. So individual turbines are designed to operate, they generate variable amounts of power at different wind speeds. And so we want wind speed, obviously, to be in the region of the power curve where they're most efficient. But we also need to think about wind direction, because that brings in interactions between individual turbines, and then turbulence as well, because if you have a lot of ambient turbulence, turbines aren't necessarily designed to operate optimally in very turbulent environments. So that's a negative. But then a positive is that if you have a lot of ambient turbulence, that erodes wakes as well. So there are a lot of interesting interactions between wind speed and wind direction and ambient turbulence. So wind speed dominates everything, because if the wind speeds aren't high enough, you can't really do anything. But then wind direction, and interestingly, the change of wind direction with height also has a role to play, because turbines don't necessarily plan on the wind direction changing by 15, 20, or even 30 degrees from the bottom of the rotor disc to the top of the rotor disc, and that can happen in some nighttime circumstances. So in summary, number one, wind speed, and then to a lesser extent, wind direction and turbulence. And then we also have to think about the grid that the electricity is being integrated into, because sometimes the grid will send signals to say, hey, thanks for offering all of that wind generated electricity, but we can't handle it right now. And then the wind plant operators have to adjust.
Thank you for that very thorough answer. And then what about the size? Is there an optimal space, like a size of a space that the wind is generated over, where you'll say, hey, the wind speeds are high in this area, but it's not high enough over a large enough space? Or is it pretty much just the footprint of the turbine that you're looking at? Is that a factor at all? The size of space that the wind is that speed over? Or is it just only relevant to that individual turbine?
Well, each individual turbine integrates the flow that is coming into the rotor disc over its a vertical extent.
Mm-hmm.
I think you might be asking about horizontal extent, and when developers or agencies or institutions like NREL do wind resource assessment, you normally try to find a region that over several tens of square kilometers has consistent wind at high wind speed. But each individual turbine focuses on what's coming into its rotor disc.
Understood.
Thanks, Julie. And okay, we got a couple more questions coming in here. And do please, if you have additional questions, we have at least 10 more minutes for questions. So please submit them in the chat. Okay. Let's see. Are details about Awaken publicly available? Can anyone outside NREL contribute to the project or benefit from the project as learning? Yes. So the place to start for the Awaken project is in the wiki link. The slides will be shared after this meeting. So that's maybe the best place to look for that link. You can sign up for a mailing list and start attending monthly meetings, and then you can learn about the different working groups. So we have a simulation group, an experimental design group, things like that. A lot of the results will be publicly available as we begin publishing results in different papers and publications. So if you're not directly contributing, then there's opportunity to learn from that, and actually all the data will be publicly available. So many places to contribute if that's of interest. Okay, let's see. The next question is there a need to improve LES subfilter models for the context discussed here, or are the existing models considered to be sufficiently accurate? Julie turned her camera on, so she wants to answer.
Yeah, well, I think that this is a fun question, and I think that people who work on developing subfilter scale models will always say that there is room for more work, but subfilter scale models do most of the heavy lifting close to the surface. So I think that it would probably, we can probably get by with the subfilter scale models that we're using now. I think a lot of the approaches are focused on increasing the resolution so that we don't have to rely on the subfilter scale models as much. And again, when we're focused on wind energy forecasting and wake propagation, we're thinking 40 meters to 200 meters above the surface. And so the role of the subgrid scale or the subfilter scale model is not as large in those regions. But I'm a professor, so it would be horrible for me to say that we shouldn't do research in this area, so I won't say that. But I think that there are lots of options of dynamic subfilter scale models or reconstruction subfilter scale models. We have a lot of options right now as a community. So it would be interesting to see if someone can make the case that this new model improves predictions at wind energy relevant altitudes enough to justify the investment. But I'm really excited that you're thinking about that. Thanks for the question.
Thank you for the answer. Okay, let's see. Another question, let's see, for Mike this time. Machine learning spans the gamut of modeling techniques from linear regression to neural networks. So out of this range of models, what kind of models are being used for the wind modeling task? Are these machine learning models entirely data-driven, or would you impose constraints based on physical laws in some way? Mike.
My camera went there. Yeah, thanks for the question, Thomas. I'd say we're using probably the full range of machine learning models right now. I mean, linear regression, probably hundreds of us go there in our daily work. My work tends to really favor ensemble-based regression trees, so things like gradient boosting or random forests tend to do the job for the needs I need. So for example, we tried to figure out from wind plant power production observations what the dominant atmospheric characteristics are that drive production. We found the wind speed obviously is number one, but then the turbulence is actually number two in terms of predicting wind power. And that can be achieved through a relatively straightforward regression tree approach. That said, I touched on some of the work Ryan King's been doing with that super resolution downscaling. And there he was using probably almost as complex as it gets. So it was a generative adversarial network where you have two very deep learning based neural networks essentially competing with each other in a way I don't fully understand. So I think we really do span the whole range. Most of it, I think it would be data driven. I think there are examples of us using some physical laws, especially Ryan's work that follow some turbulence laws, but it's sort of a range at this point.
Okay, thanks, Mike. Next question is openness to collaboration. How does one go about expressing interest? So I would say, yeah, there's depending on the project, there's probably different levels of openness, but certainly I think it would be okay to email the folks who've spoken today on the webinar. If you're within NREL, that's fairly easy to find us. If you're outside of NREL, there is a staff locator on the main NREL page, so you can fairly easily find everyone's email address. So that's where I would start there. Okay, then another question from Dries. Hi, Dries. Are there any plans in the Awaken project to make extensive measurements of the vertical structure of the atmosphere, such as boundary layer height, capping inversion strength, Not many experimental campaigns measure these quantities, but could be important for wind energy. Yes. Let's see, and Julie can chime in if I'm saying something incorrectly, but for example, we will be deploying oscillometers to measure the boundary layer height. The ARM program has wind radar profiling systems that we hope to make use of, and a lot of our LiDARs, while scanning horizontally, will also be scanning vertically to measure boundary layer height as well. So it is really of interest to see how the wind changes over the top of the wind farm, because that's where a lot of momentum is being extracted as well. And so, yes, certainly above the wind farm to the height of the atmospheric boundary layer will be of interest. And that's the last question in the chat at the moment. Oh, and Julie just had a better answer on Drew's question. So we have a couple more minutes if anyone else has any last minute questions. Okay, here's one that just came in. Let's see. Turbine level LES simulations use an inflow turbulence because boundary condition as a major uncertainty headache. Does nesting within WRF overcome that? Julie.
So there's a lot of different ways that you can nest LES within WRF. So there's a whole DOE project called mesoscale microscale coupling that is looking at methods for taking mesoscale WRF simulations on 1 kilometer scale and then nesting down to large eddy simulations. The trick is, how do you tickle up the turbulence in the large eddy simulation domain appropriately? So there are a lot of clever methods that people have used to try to tickle up that turbulence. So I think the most widely used one is a cell perturbation method, where you make small changes. You basically add noise to profiles of potential temperature on the edges of the domain, and then that tickles up the turbulence so that you don't have to wait for 10 or 20 kilometers of fetch in your large eddy simulation domain to get reasonable turbulence. So I know that there's a lot of activity comparing different methods for triggering turbulence, but nesting doesn't completely overcome it, but it does help. You just have to recognize that mesoscale turbulence is not the same as large eddy simulation turbulence. So I think that some of the people that I've seen participating in the call are part of that project. So, Matt, if you want to, Matt Torchfield, if you want to chime in the chat, by all means, please do. But there are methods where people are trying to overcome that.
Thanks, Julie. And I think we will end it there. Alex, did you have any final comments for everyone?
Yes, I just wanted to say thank you to all of our speakers, all of the attendees for your interest and your participation. You'll see in the chat where we have a link to past and future upcoming webinars. We'll be posting a calendar here shortly on that page. The recording will be there, as well as the presentation materials. Apologies for the connection issues in the middle there, but we're going to go ahead and re-record that and get that online. Please reach out to me if you have any questions, and more importantly, be well, and I look forward to seeing you on future dates. Have a great day.